Welcome to this explainer. Today, we're taking complex statistical concepts and transforming them into intuitive, totally accessible insights. Look, if you've ever felt kind of intimidated by the heavy math behind machine learning, you are in the exact right place. We're going to break down one of the absolute most foundational algorithms in data science, and we'll do it using clear, plain English explanations. So, how can we predict the future using data? It's the million-dollar question, right? It sits at the heart of almost every major industry today. We all want to look ahead, whether you're trying to predict a house's selling price based on its square footage, estimate future sales from a marketing budget, or even just guess a student's exam score based on the hours they studied. We are fundamentally trying to draw a line from the data we do know to the outcomes we don't. And the solution to all of these questions? Linear regression. Now, I know machine learning sounds incredibly cutting edge, but get this. This is actually a 200-year-old statistical technique. It's just been completely borrowed and revitalized by modern machine learning to make automated, super accurate predictions. The real beauty of this algorithm is that it gives us a highly effective way to model relationships in our data, and you don't need incredibly heavy or abstract math to do it. Here's our roadmap for today. We'll cover, number 1, what is linear regression? Number 2, the line of best fit. Number 3, how the algorithm learns. Number 4, simple versus multiple regression. And finally, number 5, evaluating model performance. All right, section 1, what is linear regression? Framing the problem and solution. Let's set the stage for how this works in practice. Picture this. You're an HR manager, and you're trying to predict a person's salary based on the years they've spent in the industry. As you look at your data, a pretty obvious pattern emerges, right? As the years of experience increase, the salary generally increases right along with it. It's a classic, straightforward cause and effect relationship. To really grasp this, we need to define our terms. On one side, we have our independent variable. This is our input, so, in our example, the years of experience. It's the factor we control or observe. On the other side is the dependent variable. That's our output, or the actual target we're trying to predict, the salary. We call it dependent because, well, its value relies entirely on the input we feed into the model. Moving on to section 2, the line of best fit, the mathematics of prediction. Let's see how this builds into the mathematical engine of our predictions. Now, don't worry, we aren't going to get bogged down in complex Greek letters or advanced calculus here. Let's just look at the simple representation of a line. You probably remember this from middle school algebra, y equals mx plus b. You might also see it written in textbooks as y equals b0 plus b1 times x. Don't let the different letters throw you off. They represent the exact same core concept. Let's translate that math into plain English, because each variable represents a very physical, visual concept on a graph. Y is our predicted output. X is our input feature. The m, or b1, is the slope. In machine learning, we often call this the weight, and that dictates the steepness, or the angle, of our predictions. And b, or b0, is our intercept, also known as the bias. Think of the bias as literally just your starting point. It's the predicted value of y when our input x is exactly 0. Now, obviously, when we first draw that line through our data, it's not going to be perfect right out of the gate. The distance from our predicted line to the actual observed data points, that's called a residual. You can basically think of the residual as the error in our prediction. If our line happens to sit exactly on a data point, the residual is 0. But in the real world, there's always going to be some distance, and our ultimate goal is to minimize that overall error across all our data. Okay, section 3, how the algorithm learns, optimization and gradient descent. Let's explore how the machine actually shrinks these residuals to find that perfect line. To understand how our optimization engine works, an algorithm known as gradient descent, imagine this. You're standing at the top of a giant, U-shaped pit, and you're completely blindfolded. Your one goal is to reach the very bottom, because at the bottom, the error is practically 0. That bottom is the treasure. To get there, you have to carefully feel the slope of the ground beneath your feet and slowly take steps downward. So this whole machine learning process, it's really just a step-by-step mathematical procedure. First, the algorithm basically makes a random guess for the slope and intercept. Second, it calculates the total error, asking itself, okay, how far off are we? Third, it takes a step downward toward the bottom of that pit, guided by something called the learning rate, which controls just how big of a step it takes. Finally, it repeats this process iteratively until it reaches the absolute bottom, minimizing the error.
Next up, Section 4, Simple versus Multiple Regression, Scaling Up and Managing Complexity. Let's dive into what happens when our problems get a bit more complex.
So far, we've only talked about simple linear regression, where one input predicts one output, like predicting weight from height. But real-world problems, they are rarely that simple. Often, they require multiple linear regression. This is where we incorporate lots of diverse inputs to predict a single outcome. Think about predicting a house price. You wouldn't just look at square footage. You'd factor in the location, the number of bedrooms, maybe the distance to the airport. The algorithm actually scales up to handle all of these multiplying inputs simultaneously to find the best fit. But here's the catch. As we add all these complex variables, we run into a massive hurdle called the bias-variance trade-off. When we train our models, we absolutely have to avoid overfitting. That's when our model is way too complex. It essentially just memorizes the training data, including all the random noise, which means it'll perform terribly on new, unseen data. On the flip side, actually, scratch that, it's the exact opposite. We have underfitting, where the model is far too simple and naive and just misses the underlying patterns entirely. Balancing the two, that is the true art of machine learning. Now, before you go running this algorithm, you need to make sure your data is actually ready for it. Think of this as your rapid-fire checklist. First, linearity. The relationship actually has to be linear. Second, we must remove noise by cleaning out extreme outliers that'll drastically skew the line. Third, remove collinearity, meaning don't use input features that are basically identical to each other. And finally, Gaussian distributions. The algorithm works best when your data roughly follows a normal bell curve shape. Finally, Section 5, Evaluating Model Performance. Grading the machine. Let's see how we assess this thing once it's built. To evaluate our model without any human bias creeping in, we rely on specific statistical metrics that tell us exactly how far off our predictions are. We start with the mean squared error, or MSE, which averages the squared differences between actual and predicted values. But honestly, more practically, we look at the root mean squared error, or RMSE. This is incredibly useful because it brings that squared error measurement right back into the standard units of our original data. Much easier to understand. And finally, we have R squared, which tells us the percentage of variation in the data that our model actually explains. Let's zoom in on that R squared metric for a second. It lives on a super simple scale from 0 to 1. If you score a 0, your model explains absolutely nothing. It's basically just guessing at random. But a score closer to 1.0, that indicates our model is highly effective, and that the independent variables we chose are doing a fantastic job of predicting the dependent variable. At the end of the day, linear regression is way more than just an abstract equation. It's a foundational, powerful tool borrowed from centuries of statistics to solve entirely modern problems. It completely strips away the mystery of machine learning and shows us that predicting the future is really just about finding the line of best fit in the chaos of our data. So I'll leave you with this one final thought. Armed with this understanding, what complex problems are you going to solve with it?